In section 2.6, we're going to take a look at solving other types of equations to include radicals and quadratic form equations. So let's first start off, let's take a look at radicals. So here are some general steps to get us moving in the right direction in terms of solving a radical or an equation that contains a radical. So we're going to have to isolate a radical on one side of the equation, all right? I'm going to say a radical instead of the radical because we could have more than one. I'm going to raise both sides of the equation to a power that will eliminate or cancel that specific radical. And then I'm going to simplify whatever's left. Okay, keep in mind that if you have multiple terms on one side of the equation outside of a radical, you're going to have to FOIL or distribute properly. If there are any radicals that still remain, you're going to repeat steps 1 and 2 over and over until you have canceled out all of the radicals. Then once you've canceled all the radicals, you're going to solve whatever's left over. Typically it's going to be a linear or a quadratic equation for what we're looking at here. If they start getting to the point where they're higher degree polynomials that are left over, it's probably something we're going to solve with a graphing utility or computer algebra software to begin with. And last but not least, we want to check our solutions and eliminate any extraneous solutions. When we are dealing with solving radicals, I'm going to raise both sides to some power, thereby increasing the degree and potentially introducing solutions that are true solutions for the resulting equation that weren't solutions for the original equation because I increased the degree. Okay, so again, you could have more than one radical. And I have a note here at the bottom that if we do have more than one radical, it doesn't necessarily matter which radical is isolated and eliminated first, but I would also caution you to take a look and see, is one going to be easier to work with than the other, and is it going to make your life simpler to eliminate one versus the other? So it doesn't necessarily matter, but it could make a difference in the amount of work that you have in front of you. So let's take a look at an example here. So here I've got 4 times the square root of quantity 3x plus 5 plus 20 minus 36. So the first thing that I need to do is I need to isolate this radical quantity here. Okay, I need to do that so that I can then raise both sides of my equation to a power and cancel it out. So I'm first going to subtract 20. We're going to have 4 times square root of 3x plus 5 equals 16. When I divide them by 4, I'm going to have square root of 3x plus 5 equals 4. And when I square both sides now, right, the square and the square root are simply going to cancel out on the left, leaving me with 3x plus 5. On the right, 4 squared is 16. Now I've canceled all the radicals, so I'm going to solve the resulting equation. In this case, it's linear. So we're going to subtract 5, and we have 3x equals 11, or x equals 11 thirds. If I were to plug that back in to my equation, so I would have 3 times 11 thirds, or 11. 11 plus 5 is going to give me 16. Square root of 16 is 4. 4 times 4 is 16. Plus 20 is 36. And this does check out. We're good to go. All right. Let's go down to the next one. So here I've got the square root of 2x plus 6 equals x plus 3. Now, I want to point one thing out. I still only have one radical here. But now, because I have an x on the outside of the radical, right? In the previous equation, when I squared both sides, I didn't increase the degree. There were no variables outside for us to increase the degree on. Here, when I square both sides, I am going to change the degree of this function. There is a high probability that I introduce an extraneous solution. It is possible that both solutions that I get could still work, okay? So you can't guarantee that one will work, one won't, but most of the time, one solution will work and the other will not. So here I take a look. My radical happens to already be isolated, so I'm going to square both sides. So I'm going to have square root of 2x plus 6 all squared equals x plus 3 all squared. Again, on the left, they cancel one another out, so I have 2x plus 6 equals, and if I FOIL, x squared plus 6x plus 9. I'm going to move my terms back over to the right here, so I'm going to have 0 equals x squared plus 4x plus 3. And now I want to ask myself, do I have two numbers that multiply to 3 and add to 4? I do. They're going to be x plus 1 and x plus 3. When I solve that, I'm going to get x equals -1 and x equals -3. Now again, here I want to go back and check. So if I use x equals -1, when I plug that in on the left, I'm going to have 2 times -1 or -2 plus 6, which is 4. Square root of 4 is 2. On the right, I'm going to have -1 plus 3 or 2. This one checks out. My second value here, right? I'm going to have 2 times -3 or -6 plus 6 is 0. Square root of 0 is 0. And on the right, I have -3 plus 3, and this also works out to 0. Right? So that equation checks as well. Now, I mentioned earlier that a lot of the times one solution will work and one will not. This is one of those rare cases where it happens to work out that both solutions work. It's not common this is the case, but it is possible. Usually one of these will be extraneous while the other one will check. So let's take a look at the next one. I have the square root of x plus 5 equals 1 plus the square root of x minus 2. Now here I have two radicals. And again, it doesn't matter which radical I try to eliminate first. I already have one that is isolated and by itself, so I'm going to eliminate that one. Right? So what I'm going to do, I'm going to square both sides of my equation. Right? So we're going to have square root of x plus 5 squared equals 1 plus square root of x minus 2 all squared. Now on the left, these are simply going to cancel one another out, and I'm going to have x plus 5. However, on the right, this is going to be a little interesting because I'm really going to have 1 plus square root x minus 2 times 1 plus square root of x minus 2. So I'm going to need to actually FOIL this out. When I do that, what we're going to end up with here is going to be 1 plus 2 square roots of x minus 2 times square root x minus 2 times square root x minus 2, or simply plus x minus 2. Okay? So at this point now, I'm going to try and move all of my terms over to the left. All right? So I have an x here and an x here. I'm going to subtract x on both sides, and actually in this case, the x is going to go away. Okay? On the right, if I were to combine like terms, 1 minus 2 is going to be -1. So if I add 1 to both sides, I'm going to have 6 equals 2 times square root of x minus 2. Now again, it just happened to be that that those x's canceled one another out. That doesn't always happen. Here I'm going to divide by 2. I have 3 equals square root of x minus 2. I square both sides. Again, the square and square root cancel one another out. I have 9 equals x minus 2, or x equals 11. If I go back and check my solution, on the left, 11 plus 5 is 16, square root of 16 is 4. On the right, 11 minus 2 is 9, square root of 9 is 3, 3 plus 1 is 4, 4 equals 4. This solution checks out. Now, when we are dealing with certain types of equations where we need to check for extraneous solutions, okay, I'm not necessarily giving points for the check on the extraneous solution, but the one thing that I am looking for and that there are points associated with, if we have a second equation or second solution, let's say we had x equals 2 and x equals, I don't know, -1/2. Right, and let's say x equals -1/2 checked, but x equals 2 did not. I want you to put an x through the equal sign, and I want you to write ext underneath of it so that you're showing me or signifying that you did check it, and then in fact you found that that solution is extraneous. I don't want you to erase it because you still should have found that solution. I just want you to identify that solution as being extraneous such that it doesn't work. So again, you're going to put an X to the equal sign and write EXT underneath for extraneous. The next thing we're going to take a look at is solving equations that are in quadratic form. Quadratic form equations are something that look and to an extent behave like a quadratic. And in particular, our exponents are going to have a pattern that follows a quadratic type pattern. Now, the one thing, let me write a generic quadratic here. So let's say I had like x squared plus 6x, and let's do minus 16. Okay, this would factor, we would get x plus 8 and x minus 2. Now notice that I don't write the exponent here on that middle term, but it is x to the first. Notice that I have a constant, and then I have that x to the first term, and my square term has exactly twice the degree of my middle term. Okay, so when we have something that is in quadratic form, okay, it could be a quantity all being squared, and then that same quantity to the first power. I could have something that is, say, an x to the sixth as a lead coefficient, an x to the third as the middle term, and a constant. And this is going to also be able to factor like a quadratic. Okay? So let me, with that example there, walk through what this is going to look like. So I'm going to have to identify some kind of a substitution that's going to make this appear to be a quadratic equation. I'm going to rewrite the equation using that transformation into a quadratic via substitution. And then I'm going to solve that quadratic equation. Once I get solutions, okay, and we're going to, for the substitution, we're going to let u equal something. Okay, I'm going to get u equals a number and u equals a number. I now need to go back to that original substitution I made. So if I let u equal, I don't know, x plus 3, okay, if I were the quantity that I substituted, all right, I need to, if I got x equals 4 or u equals 4 as an answer, I need to now substitute and replace that u with the x minus 3 or whatever the expression happened to be. All right, so I'm going to back substitute from u equals a number, and I'm going to use that let u equal an expression for the substitution above. I'm going to substitute that back in, and now I'm going to solve for x. Okay, here, if you look down in the bottom here at my example, if you notice, or if you agree, x to the sixth is the same thing as x cubed all squared. Okay, I want to be able to write essentially that lead term as a quantity or as some quantity to the second power. So in this case, I'm going to let u equal x cubed. Okay, what I'm going to end up with, and based on that substitution I did over here on the right, I'm going to have u squared plus 3u minus 4. And now I have something that is in a quadratic form. So when I factor this, I'm going to have u plus 4 times u minus 1. Or I'm going to get solutions of u equals negative 4 and u equals positive 1. My last step then, because I made this substitution here, I need to re-substitute. And instead of u equaling negative 4, really what I have is x cubed equals negative 4 and x cubed equals 1. So if I were to take a cube root of both sides here, I'm going to get x equals the cube root of negative 4 and x equals a cube root of 1. Right? On the left then, x would equal the opposite of the cube root of positive 4, and on the right here we get x equals 1. Right? So again, I'm identifying some substitution such that I can write that lead coefficient or that lead term as a squared value or quantity. Okay, then I'm going to make that substitution. I'm going to factor, right? Now that I've made the substitution and it looks like a quadratic, I'm going to factor it, I'm going to solve it. Once I've solved it, I'm going to back substitute using that u equals expression, and then I'm going to solve for x. Okay, please, with these problems, don't forget to solve for x. Now, when we have some like this where it's x to the sixth, plus 3x minus 4, keep in mind that here I could go straight to, it has to be something x cubed and something x cubed, and ask myself, well, what values are going to factor, right, to give me what I want? It's going to be plus 4 and minus 1, right? So I could have x cubed equals, let me do that in 2 steps, plus 4 equals 0 and x cubed minus 1 equals 0, or x cubed equals negative 4 and x cubed equals 1. And I would end up with my solutions then of x cubed equals the opposite of the cube root of 4 and x equals 1 when I solve them. So I can get the same answers. When it is a polynomial function, it is sometimes easier to just straight factor it than it is to do the substitution. There are going to be some equations where we're going to want to make that substitution though. So let's take a look at a couple. All right, with that being said, here I could make a substitution. I've got x to the fourth minus 8x squared plus 16. Okay, x to the fourth could be written as x squared squared. So I could let u equal x squared. Or I could just say the only way I'm getting x to the fourth is if I have an x squared times an x squared as the lead terms in my function. And I ask myself, are there two numbers that multiply together to give me 16 that add to negative 8? And I do have them there, negative 4 and negative 4. Okay, so in this case, I'm going to have x squared minus 4 equals 0, and x squared minus 4 equal to 0. Right? I can solve each. I get x squared equals 4, and because they're identical, I get x squared equals 4 again. I take a square root of both sides. I'm going to get x equals plus or minus the square root of 4, and I'm going to have that twice. And I'm going to end up with x equals plus and minus 2. Now, I'm going through and writing them both down, but really at this stage, I really only need the one, okay? Technically, it has x equals 2 as a solution 2 times, and x equals negative 2 as a solution 2 times, okay? Or I could have done the u substitution. U substitution would have given me u squared minus 8u plus 16 equals 0, which would give me u minus 4 times u minus 4. Or if I skip a step or two, u equals 4, u equals 4. If I make that back substitution, I have x squared equals 4 and x squared equals 4, or x equals plus or minus 2 and x equals plus or minus 2. So again, I get the same solution regardless of which method that I use. You may prefer one over the other, and it's totally different if you use one for a certain problem, use a different method for another problem, whichever makes the most sense for the particular equation or problem that you are looking at. So let's take a look at the next one. So here I've got x to the 1/2 minus 2x to the 1/4. This is still a quadratic form equation, but if you go back to our last section, one of the first things that I said, whenever we're dealing with solving really any type of an equation, we always want to ask ourselves, do we have a GCF? In this case, I do. The GCF is going to be x to the 1/4. So if I factor in x to the 1/4 out, I'm going to be left with x to the 1/4 minus 2 equal to 0. I now have a factored form of my expression. I have x to the 1/4 equals 0, and I could have x to the 1/2 minus 2 equal to 0. If I raise both sides to the 4th power, 0 to the 4th is still 0, so x equals 0. In my second equation, I need a couple extra steps to solve this. So first thing I'm going to do is I'm going to add 2 to both sides. So I'm going to have x to the 1/2 equals 2. And now that I've isolated that x to the 1/2, I can square both sides to cancel this out. And I'm going to end up with x equals 4. Right. Our next equation, right? I have quantity x minus 3 squared plus 6 times that quantity x minus 3 plus 8. I could FOIL out the x minus 3's, distribute the 6 into the x minus 3, combine like terms, and then hope that it's going to factor. Sometimes it will. Sometimes it won't. Here, because it's already in a quadratic form, I have a quantity squared and that same quantity to the first power followed by a constant. I'm going to make my life easy and I'm going to solve with a substitution. I'm going to let u equal x minus 3. Okay, so when I do that, I'm going to have u squared plus 6u plus 8 equal to 0. Two numbers that multiply to 8 and add to 6 are going to be 4 and 2. So I have u plus 4 times u plus 2 equal to 0, or solutions of u equals -4 and u equals -2. I still need to do my back substitution then for u. So what I'm going to have is x minus 3 equals -4 and x minus 3 equals -2. When I then solve, I'm going to add 3 to both sides. I'm going to have x equals -1 and x equals +1. Our next example, I have 2a to the first minus 5a to the 1/2 minus 3. And again, here I have something that follows my quadratic form pattern. I have a leading coefficient to a power, and I have the same variable or quantity to 1/2 of that leading coefficient's power. So in this case, I'm going to let u equal a to the 1/2. Because again, a to the first is a to the 1/2 squared. So what we're going to have here then is 2u squared minus 5u minus 3 equal to 0. Now I have something in a quadratic form that I want to try and solve. I have a couple options here. Right? There is no GCF, so I can't do anything with that. I could do a times c and go through factor by grouping. But in this case, if you notice that both the leading and trailing coefficients are prime numbers, my options are relatively small and limited. So I should hopefully be able to figure this out by brute force. I know I must have a 2u and a u for these two leading terms in each binomial. Now I know I have either a +3 and a -1, or a -1 and a +3 in some fashion here. I know I need to have a -5u, so the sum of my products for the middle term when I combine like terms needs to be a -5u. So if I make this a +1 and a -3, here I get a -6 and a +1u, and therefore I get my -5u. So just by essentially brute force, trial and error, I was easily able to figure this out without factor by group or a times c and factor by grouping. Okay, you don't have to do it in this manner. If factor by grouping, or if you couldn't figure that out, factor by grouping is going to work. Okay, it's just going to take a couple extra steps. All right, so if I go through and solve here, I'm going to end up with u equals -1/2 and u equals 3. Again, if I do my back substitution, I would have a to the 1/2 equals -1/2 and a to the 1/2 equals 3. And if I square both sides, here I'm going to have a equals 1/4 and a equals 9. Okay, so that should wrap up this section of notes for radicals and quadratic form equations. We're also in class, we're going to do a couple more problems of each type tomorrow, just to walk through and make sure we're on the same page. And I'm also going to introduce equations of circles to us as well. All right, have a good night, and I will see you guys tomorrow.